差不多。对吧？是的，是的。少这个一条。大量怎么从边？你不能只是拿着一个东西从没有地方丢了。对啊，你看你的后面那个布啊，那个布对布这样子，走在后面，他的布这样子放在中间，然后一个是往前的，一个是 go start 的这样子。我要是都准备那个笔，他都给样子够一下，一两次够了，一个假没有够一下，不行。那就最前面，是好啊。可以，这种说法也是。你注意一下，看你这个，所以它这个比较低，它这个是什么？
Hello，再见一个人。啊，这里边有你的名字。嗯嗯，年呢？全部是年呢？啊，年呢？
它是 sticker 的，然后还弄上去。
所以你这是白的本来，那不就帆布啊？
嗯，
因为把厦门的牙贴上去，是厦门的牙齿，厦门的鹅。
你所定的
这不是下雨吗？
啊？
不是我定的，
谁定的？
也有。
好吧。准备2个小时讲作业了。
那个讲一点什么的，讲一点
你到时候又让我打你 revision week 可以。你之前不是说要做附录
啊？
你之前不是说要做个附录啥的？
哦，
加了附录就超200页了。我昨天弄完正好200页了。
对。哎，我才注意到有一个东西不应该在那个 class equation 后面，
什么？
那个 group action 的东西应该把它丢去前面，
哪里？
就是不知道怎么跟是那个 significant。哦，那应该是站在我想一下 table 呢之前还是什么之后？
就放在 group action 之后。
对啊，对啊，而且应该要打进那个例子里面，为什么这个例子被拆开出来？
哪个例子啊？等会儿
就是那个他的那个 paragraph 被一个例子塞在那个。
别和我电来。没有，因为你 class equation 嘛，是瞬间的group action。
没有这种东西，这个东西应该是好来对对，而且这种东西就丢在然后里面。 在哪个 example？
没有，这个 example 是和这个一起，这是一起的嘛？
对啊，
对啊，为什么不能被分开？
没有啊，我想应该是你的课件里面应该就是先中间3个。
我知道，但是就是说
你想怎么办？
，OK，首先这整段东西你去去哎，为什么没有这一步啊？
怎么可能没有 Facebook？
哦，等等，的话，恢复之后，
那是哪？
这个之前，
就已经发一个就是这个先了。
对，
那你说那个例子要删呢？
那例子其实和这一个配合这一个的，配合这个解释，就是说，
然后
因为你看到这两个 triangle 不一样，
嗯，
来引合这两个的 group action 不一样，对吗？
对。
哎，那个放这个图片了啊，不是放那个
没有这个，
没有，他说有些空白的地方，我会塞个插图进去。
干嘛呀？
好吧。还为什么不是用你的号发给我？
现在拿我闹吧。
最好
这个
这个例子要放在这个号后面。
不是这动画就是
啊？
这个例子是为了解释，
好吧。那是先放这段话，还是先放图，还是先放图的？
我希望这段话进这个
我知道，那
进来这个地方，
进来这个 example 里面放哪？
你说要怎么排版？我想一下，
是有什么好想说的？
我想一下怎么表达。
3个字那边并没有 F 的，
因为那就是 x 本身
但是
，permutation。
X Y 也是可以啊，就是那6个东西是吗？
哦，你是说那个1、2、2、3那些哈？但是问题是，就是我们已经 prove 了，其实你相乘的时候，它会
变成 X Y 的，
就比如说 xy 等于 yx square 哈，是吧？还是哪个？yx 等于 xy square 啊？所以其实它不 free，就是 yx 会等于 xy square，对，它不 free 哦。如果 free 的话，它是可以一直乘、一直乘、无限乘下去，然后 such that 它不会重复的。
什么叫重复？
比如说1212等于1，如果是 free 的话，1212是自己。
就是 Y X 乘 Y X 不是1啊没？
对啊，那个也是其中一个哦。
哦，这样它不 free 啊？
它不 free 啊，
这样
因为它 y 如果 free 的话，y x y 是自己，就是
对啊，
就是自己就是
那如果它不
全
free 的
新的东西。
free 的话
然后我们就
才会变成一啊。
所以我们才说那个 isomorphism 嘛，把它所有的 relation 找出来。
在刚刚我说好有，但是如果可以小时，
第一个，第一个。
那我就在旁边得到。
你不是觉得很像教堂吗？可以放圣经啊？啊？没有，做没有来？
他是他在看着他的那个决定选 OK， 然后看过他就来这里。第二个他只是选他那个这个也不是一个错，那他就来。
Hello. Okay, let's start. Do you bring any question or not today? 有吗？带问题来吗？有问题有啊。OK， 这样有问题等一下问。我们先 go through assignment 先。We go through assignment first, and then maybe you can go through your question. Then we can go through a summary. Okay, comparison chart I do for you for group and rings, and then I will highlight a certain section that you need to pay more attention for exam. Okay. Yeah. Okay. So let's go through assignment 6 and 7. So assignment 6 I already returned to you yesterday. Assignment 7, unfortunately, I cannot finish because your assignment is too long and a lot of you 50. Huh? Your assignment I have to spend at least 2-3 days to finish. Okay. Yeah. 意思说你们写了很多东西。Yeah. Which is good, which is good. Just that I need to spend some time to mark. I hope I can finish over the weekend or at least next Monday. When's your exam? Next Monday. Definitely will be before next Wednesday. And then if you have any question, then you can message me. Maybe because we won't see again. I'll release the solution also. I already released solution 6. So later after this class, I will release solution 7. So you can read solution first, and then I'll give you feedback for 7 later. Okay, makes sense? Okay. Okay, so let's discuss assignment 6 first. So, well, I mean, actually, I gave a lot of hint for assignment 6, right? So, for those who follow my hint, doesn't do quite well. Okay, do quite well. But some of you didn't discuss the main point that I want you to discuss, so I cannot give you too many points. Okay. All right, so for first question, symmetric group S3, add on 2 sets of order 3, and then we try to decompose it into orbit for this diagonal action here. Okay, so discuss 2 cases where first on U and V are transitive, and then the other one on U is transitive, but on V is a 2 split orbit here. So before discussing this diagonal action, you actually need to tell me what's the action of G on U and V first. Okay, you have to do this. Okay, but to do this is what we discussed last time, no? Whether so you can define action on the transposition first, right? Because transposition generate S3. And then you tell me what kind of action can be done by this transposition. Either what? Either they do act like an identity, or they act at the same transposition, or they act differently. So these 3 cases here. Okay. Only 2 cases needed for this two cases here. So transitive action means what? The two transposition might act differently. Okay. If split, the two transposition might act the same way. Okay, so you need to discuss this. But in this solution here, we will talk about this three type of action using the kernel of the group action. Why we use the kernel of the group action? Because we know that the kernel of a group action is a normal subgroup. Because group action is a group homomorphism. Remember, I give you a group action, there's a one-to-one correspondent to a group homomorphism. Okay, so actually you discuss the type of normal subgroup exists in S3. Okay, so if you discuss the type of normal subgroup in S3, there are three types here. So which is identity, A3, and S3. So this three also correspond to the three cases we discussed last time. Okay, if my kernel is identity means what? All the elements will act differently. If my kernel is A3, actually this will correspond to the case where the two transposition act the same. Okay, and then if every acting in S3 act like an identity means what? This action is trivial. Okay, so this is a different way to talk about the three possibilities. Okay, so once you talk about this, you try to split the orbit of the diagonal action here. Okay, so two types. So in the first type, if it acts transitively, the orbit will look like this. So it splits into two parts here. So first part is where I and j is different. The other part is where I and j is the same. Okay. Yeah. So up to labeling. So you should send sigma ui to sigma I. So this part is quite how to relabeling. So here there's a typo. Okay. Okay, so the main point here is this. Because sigma is bijection, if I and j is different, your image will also be different for I and j. This is the main part for to explain this orbit here. Okay, because it's bijection, right now. Because the contrapositive is true. If sigma I equals sigma j, you can take the inverse such that I equals to j. Okay. And then second part is you will split your two orbit into P1 and P2 such that P1 is fixing Vi, okay, and then include all the possible Ui, and then P2 is all the Ui Vj such that j equals to 2 and 3. Because the orbit for V is just the orbit for V is just Vi P1. Okay. So actually in class, I gave you this whole part here. What you left to do is figure out what's the orbit. Okay. Second, I think second everyone did pretty well. Okay. Just that one thing to note here is this part here, part 2 here. There's two directions actually. Okay, most of you only do one direction. Okay, most of you only do the forward direction. Actually, the backward direction is trivial. Okay, if G equals to E, then EX always equals to S. But you didn't mention. Okay, make sure you mention it. Hello. Yeah, I think this question is pretty well. Part 3 here. I realized I think most of you didn't get my hint in my class. Is it? You didn't get my hint. Actually, I gave you half of the solution already for this question here. So here, acting here includes well-defined. So actually, when I ask you to show it act faithfully, right? There are two parts here. One is faithful, one is well-defined, the other is faithful. And then to show that n is equal to kernel phi also have two parts. We also have two parts here. Subset equal two dimension. Other than that, it's just playing around with definition. Okay. Question 4. I think mostly is good. Mostly good. Just that when you write out these compute this calculation, right? Make sure you either draw it or you use algebra way to write it. Okay, don't just simply tell me they are equal. Okay, so justify more. And then last part is to give counterexample. Again, the second part. Make sure if you say that two things is not equal, again, not true for all function, you have to give counterexample. Make sure you give counterexample. So if you don't give, I'll just take off your mouth. Yeah. To show that something is not true in general, you need to give me counterexample. Because for all is true means what? Negate for all is true. There is something that is not true. So you need to show the existence. So you need to give counterexample. Okay, any question on this part here? This assignment? Any question? Any question? No. I think this assignment, a lot of you got full mark actually. In particular, I saw improvement from Jiayi, Wang Jiayi. Yeah, quite good. Yeah. 谁来的？来介绍一下王嘉怡，可以举手一下吗？王嘉怡 ，OK， 好。这次我觉得他进步很大。啊 ，Menchun， 你说吗 ？Menchun 呢？你觉得你考试会考得好吗？啊，够用啊。但是你 assignment 不好，我不知道你考试能不能救到你。
包火脚包到没有
OK，
把太多人去包，还有包堆脚。
OK， 我觉得你的 assignment 不应该要那样坏，但是就很坏，所以就所以考试要考了。OK， 一凡一凡你的答案呢？你都是从 ChatGPT 来的啊？不是？你那边写我是从 ChatGPT 来的。OK， 怎么你不要看我的嘞？我的干嘛？我却比 ChatGPT 乱！我操！你应该要看我的、啊，我有给你 hint 啊，我大半题都给你了。对啊，对，你应该看我的，对不对？你看我的，然后再看 ChatGPT 的，对啊，因为我不可能害你的嘛。对啊，我一定跟你讲答案的。相信，就是我有一个故事啊，不知道告诉过你们吗？我的学生拿我的 assignment 去卖800块。问题是那800块又不是满分哦，懂吗？这才是最大的问题。你钱花了啊，债也还没消，这样有什么办法？你知道吗？你觉得有什么办法？对，把800块给我，我可以跟你讲答案，对不对？我要教你啊，对不对？我教你啊，肯定答案对吗？对不对？你给我800块，好 ，OK。下次钱太多不是给我，钱太多给我，不要给别人。OK。Okay, next. Assignment 7. All right, assignment 7. So, assignment 7. Okay, first, find the kernel. Okay, kernel of these homomorphisms. So, part 1a. So, you want to find the kernel such that you map fxy to f00. What does it mean, fxy to f00? Meaning what? You substitute x and y to be 0. Then when is this polynomial 0? if all the terms contain x and y is already 0. Only when the constant term is 0. Okay, so meaning what? It have to be generated by x and y. Okay, so to show it, you need to use division with remainder. Okay, you divide by x first, you left with polynomial in y, and then you divide polynomial in y. Polynomial in y by y, then you left with constant, and then you need to evaluate this polynomial to 0. Okay, so the constant term must be 0. B, so B sends x to square root 2 plus square root 3. So if you note that actually this is the irreducible polynomial, okay, for this root, such that it evaluates to 0. So how to prove it? So my argument here was you cannot find a polynomial of lower degree with square root 2 plus square root 3 as a root. In particular, you check that x minus square root 2 minus square root 3 squared and x minus square root 2 minus square root 3 has summing square root 6 and x. I mean, actually, this is one way to say that the terms are linearly independent. Okay, so I let you assume that 1 and square root 2, square root 3, and square root 6 is linearly independent. Yeah. And then part C. So look at this morphism here. I send x to t, send y to t squared, send z to t cubed. So well, you can build some polynomial, right, such that they evaluate to 0. For example, y minus x squared, z minus s cubed. Actually, you can get the third one, right? What's the third one? Can you get the third one? Y squared minus z, y cubed minus z squared, z minus y x. Oh, also can, right? Also, you can do y cubed minus z squared, right? Also evaluate to 0. Okay. So the question is, how many generators you need? Okay, so how many generators you need? Turns out that you just only need 2 of them. Okay, you also use division with remainder. You know? Does it make sense? Okay. Some of you ask why I directly write like this, kernel of V. Actually, this one is claim. Okay, you need to prove. Okay, it's not that how to say, I guess this, I'm guessing the solution, but we still need to prove. So the bottom here are proof. Okay, so once you write something down, you need to prove. It's not that, okay, I don't know how to say. It's just that, So, I mean, 我就问你一个问题啦 I mean, like, 如果你写多 let's say 你写多 right? Let's say 你写多something like that. 你一开始 claim 是这个，但是你 proof 一般般，其实觉得这个东西没有用。Then what do you do? 删掉它，就删掉它 ，as easy as that， 就这样吧。不要以为说你写了什么就是一定要那个还是什么的 ，It's not like that. Okay. 这就是你要 prove 咯 ，That's why we need to prove 咯。Okay, that's why I need to prove. After proving, actually don't need the third one. Okay, remove it. Yeah. 哎，那天好像李亮有问过一个问题，What did you ask me Replace 这个 C with 什么东西？你问我你是有问我R Yeah, sure. You can replace this with R. Doesn't matter. 没有问题。应该可能还是一样。也是linear 一样，没有什么问题。没有什么问题。你 replace with R 也没有什么问题。还有吗 ？Yeah， 没有什么问题。Because our argument actually happen in domain, they are linearly independent over that. Yeah. Because our probability is Z. Okay. Okay, next two. Identify the following rings. OK， 很多人有问题哦，问题就是说 ，if I want to reduce this 啊，我几时可以停？我要停在哪里？对不对？我要停到什么阶段？对不对？你们的问题。比如说，我给你一个分数啊 ，I give you a fractions。OK，if you want to simplify the fractions，你要停在哪里？Let's say 100 over 1000. You simplified it. 10 over 100. 可以停吗？ Why not? Come on. Divisible. So you mean there's more, still have common factor. Okay, you can reduce such that the common factor is 1. Okay, so in this case here, 这边的 cases, what do you reduce to? Okay, so 看一下 So first is z mod 2z adjoin some root, and then second is z mod 3z, third is z mod 3z, or if you do the other question, z mod 7z. Then last one is z mod 5z, adjoin another root. Okay, so where do you stop? You can stop as a, how to say, where do you stop? Where should you stop? You stop. How to say this? Where do you stop? Okay, like what do you do for the quotient group? Do you remember the quotient group exercise? Where do you stop? Do you stop at the set of coset? Or you find an isomorphism to some simple group? But in this case, you also find an isomorphism to a simple ring. Okay, and maybe the kernel that you left over, you can try and make it an adjoint. Make it an adjoint. Still remember the adjoint idea or not? Adjoint. Adjoint idea is some. When did you put adjoint? One example you have to remember is about this C here. Okay, C here we will write R adjoint I. Now what is really R adjoint I here? This is the polynomial ring Rx such that it is quotient by x squared plus 1. Okay, so whenever I draw this isomorphism, you need to tell me the map. What's this map here? Sending x to I. Okay, and then such that this kernel is what? X generated by x squared plus 1. You need to show like what you do for question 1. Show that, okay, the kernel is x squared plus 1. Obviously, this I is not any, not any variable. This I have to remember it satisfies x squared equals to minus 1. Okay, if you can imagine if this x is random x, this is, isn't it? This is the same polynomial ring. Non-meaning one. So you need to be careful. Whenever we put I, put something else, you need to ask the person, this variable got satisfy extra condition or not? Or it's just a random variable. If random variable, that means polynomial ring. Okay, otherwise it will be some quotient ring. It will be some quotient ring. Does it make sense? 懂我在讲什么吗？adjoint 这个东西很重要它如果有 satisfy 一些 relation 的话，它就是一个 quotient ring。如果没有，才是一个 polynomial ring。OK 吗？明白我讲吗 ？OK， 因为你看我们 algebra 是这样的，我们可以换 variable 的，比如说我可以换成这样 y square， 然后隔壁这个我换 x， 也是可以的吗？把 such that x square 等于减1，然后这就是我们的 I 了，就是我们所熟悉的 I。So you need to be careful. So you need to know whether check whether the variable satisfy further relation. Okay. Okay, 通常 usually if we don't write it out, it is just a normal polynomial ring. Okay, for I, 就算我们没有把它写出来 we like assume you know. You understand? 就 assume, okay, assume you know that there's a complex I, 不是一个 random I. Okay, so let's go into this question. So first, you try to identify these two rings here. Okay, so if you try to find the coset thingy, right, you'll find that there are much more things to reduce. Okay, so much more things to reduce. So one technique for this kind of question, right, you should ask yourself, is there any other jointer inside this ideal? Okay, such that you after the quotient you reduce this ring much more. So for example, in this case, you will see that 2 can be generated by these two polynomials here. So meaning what? Meaning you can quotient by 2 first, okay, and then do the other quotient. Look at this ideal here. If you quotient by 2, what happened? 2x plus 4 is already 0. Okay, so you left with x squared plus 1. So once you reach x squared plus 1, you cannot do anything more actually. So you need to adjoin the root of x squared plus 1. Okay or not? But not that x squared plus 1 in. Okay, so let me write here first. So there's a tricky point here I want to tell you for this question here. So let's say this is equals to zx quotient x squared minus 3 2x plus 4 and 2. Okay, then this is isomorphic to the MAT2 that x adjoint x squared plus 1. Note that 1 is also a root for this polynomial. 1 squared plus 1 is 2, which is 0. Okay, but you cannot adjoin 1. Oh. You know why? You know why? Don't know. So let's say you send x to 1. What's the kernel? You need to ask yourself, what's the kernel? Okay, what's the kernel? So if you look at this map here to sending x to 1, what's this kernel here? Actually, the kernel of this map, right, is what? X plus 1, not x squared plus 1. Okay. It's a bigger ideal. Okay. So you need to ask yourself, which homomorphism that has kernel x squared plus 1? Whose? So actually, you need to send x to a imaginary number I. Okay. Such that this group is isomorphic to Z mod 2 adjoint I. So I is the one that satisfies I squared plus 1. So I plus 1 is not 0. I plus 1 is not 0. So here you should note that I plus 1 is not 0. This is the extra root that we introduce. Okay. Yeah. But why it makes sense? Why it makes sense is also because of this. If you compute the set of coset of this quotient ring, there are actually 4 things on it. 4 things here. Can you see why is it 4 things? Can you quickly see why the 4 things here? Z mod 2 zx quotient by the ideal s squared plus 1. Quotient by s squared plus 1 means what? Sorry. S squared plus 1 is equals to the 0 polynomial, right? Okay. So what's the lower degree than 2? What are the polynomials that have degree lower than 2? 0, 1, x, x plus 1. That's all. Because z mod 2 z, the coefficient only 0 and 1. Okay, no. So if you do Z mod 2Z, adjoint I is also the same. What are the 4 elements here? 0, 1, I, and I plus 1. Okay, so this is the corresponding one. So 0, 1, I, and I plus 1. Okay, but hey, isn't it I just changed variable, man? Then what's the business of isomorphism here? Now I'm teaching you how to see this isomorphism. So what's this business here? Why isomorphic? Just change your variable, man. Why isomorphism? Actually, this set is set of coset, you know. Set of coset. Okay, inside here actually should have bar 1, 0 bar, 1 bar, x bar, x plus 1 bar 1. Okay, but on the other side, it's just elements, like how you treat complex numbers. You know? Yeah, actually go bar. Actually, these elements go bar on the top one. Okay. Question? Question? So why we remove bar is like when we learn the free group one, we don't put bar on top of the word. But we know that it is a group of equivalent classes. Yeah. It's the same idea. Okay, no? Okay. Okay. For the other question, I think you have question or not? Actually, I have marked your assignment. The other question is similar idea. 有问题吗？还是你看的时候你不用讲多，那时候现在我可以教你点做。啊？拍的时候问看。expiry date 是 final 前 ，voucher expire 了。But I mean, yeah. So I mean, 我教你的 technique 就是看一下你能不能把号码做出来，从你的 idea. If you can build an integer, then that means you can quotient by that integer first. Because quotient by integer is always easier, right? You reduce the coefficient. After you reduce the coefficient, then you start reducing all the polynomials. Okay 吗 ？OK。我觉得你们要小心的是最后这一步，这种 adjoin 那个 root 的时候，你要小心。什么时候 you can adjoin 一个 root？When？ 不知道。舒瑶呢？这个很重要。什么时候可以 adjoin 一个 root？ 洪瑞耶？洪瑞会吗？什么时候我们可以写 R adjoin 一个 root？When？ 什么时候？什么时候我们可以写 R adjoin 一个 root？ 什么时候？什么时候我们可以这样写？你不只要检查这个东西哦，不只要符合 root 的这个equation， 你还要符合什么？这个 isomorphism。所以这个 isomorphism 是什么？所以你要讨论这个 isomorphism 是什么，肯定要把它右边写出来嘛。它右边是什么？右边是什么？右边是什么 ？OK， 我给你这个 isomorphism 的名字啊 ，Let's say call it phi。它右边要是什么？一个 polynomial ring portion out by the f。这个 f 是什么 ？OK， 我终于知道要讲调整它定义了。OK， 这个要切by 什么东西 ？Kernel of phi such that what? Kernel of phi is equals to the ideal generated by f(x)。这个条件 ，OK， 你看有几个条件在这边，我们 list 下来，一个条件，两个条件 ，two condition you need to check， 对吗 Okay, sorry，就这样。OK， 但是在 general 也没有问题。OK 吗？哪里不 OK？来问。我再解释多一次。OK。So how to write? So how to write R adjoin a root alpha such that alpha satisfy f alpha equals 0? What do? You need to build this homomorphism, okay, from the polynomial ring R adjoin X, such that the kernel of this homomorphism is what? Is the ideal generated by fx. Obviously, 这个 homomorphism have to be surjective 啦 ，but 看得出为什么它 surjective 嘛？OK， 其实这个 homomorphism kind of fixed already， 已经被 fix 了。应该这个 homomorphism 长怎样啊？应该要是什么 ？x 送去 alpha。这个 homomorphism 有一个名字叫什么 ？evaluation homomorphism。为什么 evaluation 呢？因为我 replace x by alpha。So this map should be surjective. Why? R come from the same R. Alpha come from X. Surjective. Okay, I reach everything inside the full domain. So now the problem is kernel. Kernel 是谁? Okay. If this kernel is generated by this fx, then we have this isomorphism. Only then you can write down this Rx quotient by this kernel of phi is isomorphic to R join alpha. OK 吗？有两个东西要 check 啊，记住两个东西。One, this alpha have to be the root of this generator. Second, 这个 isomorphism 要存在，这个才是 trick。怎样 prove 这个 isomorphism? Two things, right? Surjectivity and injectivity. So surjectivity 我 explain 给你听啊。So injectivity 在哪里？Kernel of this phi must be generated by the then you can use first isomorphism theorem to get this result. So actually it's by first isomorphism theorem. 1、2加上 first isomorphism theorem. Okay, maybe 就1、2、3啦，这样的话1、2 then 3. Okay, so here is a first isomorphism. OK 吗？有问题吗？这个很重要啊，这个 adjoint root 这个，就这样吧，没有什么特别啊，很重要，对，很重要。OK 啊 ，Yeah。OK， so 第3题 ，so prove that I contains a monic polynomial of degree and if and only if it is a principal ideal. Actually， 你们只要写一个 counter example 就可以了，不是？还有一个方向是错的 ，which direction is wrong？ 啊 ？Which direction is wrong? Left to right, right to left. Right to left， 画一下。So 如果这个 direction is false means what? If it is a principal ideal, it might not be generated, might not contain a monic polynomial of degree n. Yeah, okay. So what you need to show for this counter example? Assume that it is a principal ideal domain, but it doesn't contain a monic polynomial of degree n. Okay, so very easy lah. You just pick ideal generated by 2x inside zx. So my direction contain, my proof contain the other direction. So the other direction is true. If I contains a monic polynomial of degree n, then it is a principal ideal. 这个东西我们 proof 过了嘛，在班上 we proved before, right? We proved before, right? Actually, this is the content for the statement for the proof of what? Proof of polynomial ring over F is a principal ideal domain. So all the ideals there is principal. Why principal? Generated by monic polynomial. So what's the proof? Use division with remainder. Because division with remainder in polynomial ring work for monic polynomial. Okay. Question 4. Okay, question 4. Prove the intersection of ideal is ideal. Okay, I think this is kind of standard question. Like proving subgroup intersection of subgroup is subgroup. B is tricky, B is tricky. So show by example that a set of products xy such that x is in I, y is in J need not be an ideal, but the set of finite sum of product of element is an ideal. Then this ideal is what's called the product ideal. Okay, product ideal is very important in future. Okay, so you need to include all the finite sum. Okay, all the finite sum, not just taking the product between I and J. Then what can you say about the relation between IJ and I intersect J? So basically, you have one inclusion here. IJ live in I intersect J. The other direction is not true. Exactly by B. Last question, are these two isomorphic? So how do you do it? So one solution you can have is you can show that there's a square root. So Z has a square root. 7 has a square root in the first ring. Okay, but it doesn't have the square root in second ring. But I think you have different solution, right? You have different solution. Yeah, what do you do? I think. Okay, 2 is invertible in the second ring, but not invertible in the first ring. Okay, because invertibility must be preserved under isomorphism. Okay, if there's an isomorphism. Any question you want to ask about your own solution? I haven't gone through your solution yet, so if I go through, I will give you feedback. Anything you want to ask? Oh, this question. Yuma, Lydia. 哪一个？哦，用眼睛看，你知道有没有 idea? Well, let's see. I mean, 第一个你要猜的东西应该是它不完东西。Why? Because 两个 idea 都不一样。You should realize that actually 第一个 idea 大过第二个 idea。我想想，有大吗？大 ，sorry， 给我想想，谁比较大 ？OK， 我不要讲大了这个东西，那边啊，我不会讲大 ，sorry， 因为他们都 infinite。So you see， 这边 it is a multiple of x squared plus 7。这边 the other one, okay, sorry. First one is a multiple of x squared plus 7, but the other one is a multiple of 2x squared plus 7. Okay. Can you build one jointer from the other or not? Seems like cannot. Okay, so you should guess that these two ideas are different. So potentially, if you quotient by different ideal, they should be different. OK，but obviously 有时候他们会切出一样东西啦，不是 exactly 一样啊 ，maybe just isomorphic 也是一样啊，在我们世界 ，we don't need to be 准一样的。In our world 啊，maybe in ring 啊，in group 啊，we only care about isomorphism，乘法一样就好了。有 bijection 乘法一样就好。not exactly equal one。And does it make sense? Yeah. 对，你先猜不一样，然后你去 try 看是不是真的不一样。然后你 try 到一半，哎，好像它要一样了哦，但可能你就 know how to build your isomorphism 了。其实是这样子的，对吗？或者如果你猜有 isomorphism，直接 build 先 build， 你觉得哎卡卡的，这边好像 prove 不到哎，可能这个就是它不是 isomorphic 的原因了。啊，Does it make sense? 呀，是这样子的。如果是你就收到了哦，不是可能那个就是它会出问题的地方，那个就变成你说它不是的地方。因为哦，这个 this is a real story, you know, there's a real story here. So there's a person called Yao 啊，什么？ There's a person called Yao, okay, a mathematician called Yao. Yao is trying to tackle one conjecture called the Calabi conjecture. Okay, Calabi conjecture. Okay, Calabi conjecture. So Calabi conjecture, how tackle it? He think for about 3 years, and 3 years, yeah, about this counter example. 他很兴奋，他跟他老师讲 he tell his master. His master is Chen, CHEN, Chen先生 yes, Chen. OK, Chen 听了说后，哎，很开心啊，感觉做 FYP 这样啊。老师听了很开心啊，老师说来我 seminar, come to my seminar, tell the expert. OK, tell expert. Calabi 也在 ，Calabi 本人在 ，Calabi 听了过后 ，OK, I'm impressed. 但是 Can you explain this part to me? OK， 要回去想，哎，解不了哦，好像卡了哦。他讲我拍死 ，he's embarrassed. OK, so he spent another 3 years to fix it. You know what happened? Turns out that he proved the conjecture. Yeah, he proved the conjecture. So 他 start with a wrong， 真的很正常的 ，start with 错的东西。And then turns out that 可能那个就是 the technical point he tackled. Then prove well. Then the thing that solved this conjecture is called a Calabi metaphor. 妖，你知道妖是谁吗？ OK， 妖是邱振东。He is a head of department in Harvard Mathematics. That US institute is led by a Chinese mathematician, or more precisely, Hong Kong. But now he already go back to Tsinghua. He already retired as a Harvard. Okay, so it's normal one. So if you predict wrong, and then maybe you work in the middle, or realize that actually this is the technical point. Okay, normal. Okay, any other question? 其他问题吗 ？About assignments. 老师说什么 ？OK， 下1个小时会告诉你。我要进广告。Okay, yeah. Oh, another thing is the notes are ready for you already. For the lecture notes, the typeset one, and then the chapter 0. So chapter 0, when do you need to read it? Is when you start. When I try to refer to previous knowledge, you can go back and refer. Okay, no need to read chapter 0 actually. actually because they are like 不是讲sorry 就是说不要来怎么说呢 ？Don't get me wrong， 不是说你不用读啊，就是说有用头才去读。很重要，其实很重要 ，OK。But I assume you know. But if you don't know, please go and read it. But 不要 spend 太多时间在上面。就这样。OK。什么？有用，很有用，但是你不要花太多时间在上面。因为感觉上次赵瑞不明白他做 revision 他从那边开始读，我不知道他要读到几时，因为我的 note 已经差不多50页了，所以我感觉他的重点犯错，我就懂。Yeah， 说哪里？
你把 chapter 名加起来就没有上。
Yeah, so if we add out all the arting stuff to excel in my class maybe you need 400 pages of it. Okay. And make sure you do people already type for you Okay, please at least appreciate their work So if you find any problem, you can contact them or contact me. Okay. All right, so let's take a break until 3 o'clock. We will come back for summary. Hmm? 不能乱说。什么来啥？
讲到一个，是一个。
他什么都没有讲过了，哦，对呀。
因为我觉得你们应该懂出来。
这边是在 average 你看，可以，对 P 要100 ，Algebra
哦，看见了，
看见真不要换手机，把这个谁那边，
看到这个东西，我知道了。
L 多，我觉得对 P 如果它小的话，
那个是1。你跟7呀，你跟7。
对，应该我想起来是。
对，
这个是 N 除 P， N 除 P 的理数是，因为它 N 才会去零，然后 P 也要去零，所以要 N 为除 P 的 N， 所以 N 除 P 啦，对，然后 N 如果除 P 了过后为什么会？N 除了 P 过后。
我跟你觉得一模一样。
这一个大牌，因为证明到高烧这个是笔记的嘛？我感觉不是打的，打的也是这个，打的只是这个反向，其他都一样。对呀，对呀。是不是你要这么写两个一样的东西？改过啊，在这里的话，我应该我是没有 update 进去的嘛？我看一下我哪个，因为我觉得 P 要 check 一下
n 然后 P 又是 n 的倍数，
等一下
对 n 能被 n 除，
，lecture 13啊，15还是13？
不知道，
15啊。
15还是13？
我觉得是 exactly P 跟 m 的关系啊。
13
改了，我改了，我没有 update 是吗？我改了这边。
没有。
呀，我没有 update 是 n 除 p，
不
我改了。
对，我们看 typeset 的是这样的，对
对对
，typeset 没有问题。
改了，其实有很多条件，
这个又错，
这个又错。
2个重复啊。
上面 P 除 m 啊
连这个是 p 除
，P 除
n，
n，
这个是对，
对啊，
什么？
是不是我讲？
这个比较清楚啊，
它这两个情况重复啊。
对啊
这个比较，清楚啊。
没有 typeset 就是打这个，
OK，
没有问题，没有问题。
但我是还没有更新到那个，真的。
手很抖哎，够力哦。
是对吗？哈，它现在是对的哈。
我没有更新到那个
我觉得 P 是 exactly 等于 m，
这个，
对，
P 也是
因为 P 能除以 m，所以 P 只是小于等于 m，但是小于 m 的 P 是不可能 mod m0啊，
mod m0是什么？哦，mod m0，
对，
OK，
所以就不可能，所以 P 一定要等于 m， 所以 P 等于 m， 但是我们把
这个 p 要等于 m，
对，如果 P 能除 m 的话，since by 我们的
讲 P divided m， 那 P 一定要等于 m。
对，
啊？为什么？
因为 P divided m 代表 P 小于等于 m，
然后
但是小于 m 的 mod m 不可能等于0啊。
哦，这不要 mod m 等于0。哦，
因为你摆上去是它的 order 啊 P，
哦，
两个都要去0啊。
哦，
但是重点是现在我 mod n 它也等于0，所以
OK，
P 是 n 的倍数，然后 P 也等于 m，
哦，
所以 m 能被 n 除，
所以 p 一定要是 m， 你是说？
对，然后 m 能被m
如果
能被
p 一定要是 m 的话，
那就是
然后
m 等于 nk 哦，啊，就 n 能被 n 能除 m 哦，
m 是 n 的倍数。
n 可以除 m 的倍数，是吧？p 等于 m， 然后
你看
p 等于 m，n 除 m，
没有，你看下 m，
所以你说更快到这一步是吗？
对，
哦，更快到这一步。OK，
我昨天找到更加快 ，m 等于 p 等于 nk 嘛，我当 k， 对，
m 等于 p
等于 nk，
等于 nk 等于 nk。
把它
OK， 呀 m 等于 nk 对啊 ，OK， 然后
m 等于 nk 就代表 m 能被 n 除啊，
m 可以被 n 除，
因为 m 除 n 等于 k 啊，
是 n divided。
OK，
所以 contradict 哦，后面有 common factor，
OK， 这样也是 n 哦
就 GCD 不等于1啊，
，OK， 啊，
这样快哦，从这里就出来了，
OK，
要改掉，这个很乱，
OK，
看一下有一次查，
OK，
我好几个有会
让你写下来，现在发给我，
是哦，
你写下来，发给我，写下来发给我，我去洗手间啊。
不是讲话。
什么？
这里有个
在这里面读。
不用读，不要花太多时间。
那这边不好。
可是这个视频本来就是在让你体会错的东西。那他们一整天
对啊，很乱啊，看得很乱。
错的东西。你要闪黑的片，你要闪吗？给他改吗？
哦，
反正你改了我就要改，打完就打完。没打吗？还有。对呀，我觉得那个想念，我不信，对方。
哇，
那么别人可以戴个片手套，那个这个鞋，还要穿手套、穿鞋，
哎，所以你澳洲的教堂是这种教堂式的，还是那种回家的那种感觉？
教堂，
就是那种国内比较风格强的。
我那边比较少电屋，
啊？我说国内很少见美家那种风格，
那种电屋啊，电屋啊，
就
还是那种现代化
现代
啊，对。
国内感觉都很传统。
来，我要开始了，来，我要开始了，等下先给我啊。OK。噔。哦，before that 还有其他 lecture 的问题吗？读完了吗？你们有没有读完？读到哪里了？读到哪里了？读到哪里？地方？什么？差不多。哦，差不多是哪里？差不多是哪里？23到，哎，28不是完了没？28完了啊？其他人呢？读到哪里了？哎，好像听说你们从拜一就开始读了，哎，有吗？有人从拜一就开始发 message 问我东西了。现在 how much you read already lecture now? Haven't start? Start? Okay. Yeah. Okay, right. So let's do a comparison chart with groups and ring. So these are the two main things we learn. So in the meantime, I will tell you what to. So right. So groups and ring. So what's the definition of groups and ring? What's the definition? Both of them are set. Okay, so they are set. In group, what do you have? You have one LLC, okay, with one LLC. Let's call it multiplication. But ring have two LLC. Okay. So two LLC are what? We call it addition and multiplication. Okay. So in groups, what does these else here to satisfy? Associative, and then identity exists, and then inverses also exists. Okay. So there's one more condition here. It's about if the LLC commute, then it is a billion. Okay. But rings under addition, okay, under addition, R should be a billion. It's an abelian group. So meaning what? For rings, under addition, you need to have every property in the group. Plus what? The multiplication has to be associative. Multiplication is associative. Also, we assume the ring we look at is commutative ring and has identity. No need inverse, no? Okay, no need inverse. Third, you need to tell me how the addition and multiplication work together. Okay, so meaning the distributivity law will hold. Distributivity. Okay, so if there's identity inside, so if there's identity, if there are multiplicative inverse exists for all non-zero elements, means what? This ring is called a field. Okay, so this will imply this ring is field. Okay. Obviously, you need 1 not equal 0. Okay, 1 is not equal to 0. Yeah, multiplicative inverse. Then, what's the next thing we do after group? Subgroup. Okay, so what's a subgroup? A subset of group that satisfy group. Okay. So similar to subgroup, we can define subring. Okay. So what is a subring? Also a subset of a ring that satisfy ring axiom. But there's a special condition here. The multiplicative identity must be the one that comes from the ring itself. Okay. Then after subgroup, what's the main subgroup we want to look at? Okay, maybe, yeah. What's the main subgroup we need to look at? What? What's the main subgroup we need to look at? 看过什么 subgroup? Normal subgroup. Okay. Normal subgroup says what? A subgroup is normal if what? 来考一考。金星 a normal subgroup N is subgroup N is normal in G if what? Conjugate what? In N. Again, if in N is a subset of N. Okay. So what is the correspondent thing in ring? It is what we call an ideal. Okay. So the correspondent thing in here is an ideal. Okay, so what is the ideal? The subset of R such that it is closed under addition and closed under multiplication by what? By the element in R. So what's the similarity between these two? What's the similarity between these two? 都可以拿来除 or in other words, what? They satisfy the kernel property of homomorphism. Correct or not? If I send phi n to identity, do you send phi g n g inverse to identity or not? Correct or not? Because homomorphism tells you what? Phi g n g inverse is what? Phi g times phi n times phi g inverse. But phi n is identity. So you're left with phi g n, phi g inverse. But you send phi g inverse to the inverse of phi g. So they cancel. The other side, if phi of I is identity, is phi of Ri identity or not? Because phi Ri becomes phi R times phi I, no matter where I send phi R to. Okay, we haven't talked about homomorphism, right? So later we'll talk about homomorphism. But there are differences, a bit different here. So I put a warning here. So a normal subgroup is a group. Yes, normal subgroup is a group. Sorry, it's a subgroup actually. But an ideal in general is not a subring. Okay, so 这个是它们的差别. Okay, might not be a subring. Because the multiplicative identity might not come from the ring. So. And what other subgroup we have seen? Okay, what other subring? Subgroup we see. So we have seen cyclic subgroup. Okay, so cyclic subgroup looks like what? A group generated by one element inside of G. And on the other side, we will have principal ideal. Okay, so principal ideal also generated by one element in R. Okay. But what's the definition here? So what does it mean by a subgroup generated by A? So these are all the integer power of A. But ideal generated by A is all the multiple of A. Okay, so next, what do we have? So here, what's the use of cyclic subgroup here? We'll see that every subgroup of Z is cyclic. Okay. Then what can we do here? Actually, we can do division with remainder. Okay. Because of this fact, or actually because we can do division with remainder, every subgroup of Z is cyclic. And more than that, you know what's the generator? What's the generator? Generated by what? Actually, it is generated by the GCD of all the non-zero elements here. Okay, so GCD is the generator. How about principal ideal? Here we have a parallel story for the polynomial ring over field. Okay. For every ideal in F adjoint X is principal. There's a parallel story here. Similarly, we can do division with remainder here. Okay. Not just monic, okay, not just monic, because we are dealing with field. Okay, so we can invert every number, non-zero number to identity. So what's the generator here? What's the generator here? This is generated by the unique monic polynomial of the smallest degree. Okay, of the smallest degree. Yeah, no. Yeah. Okay. Can you see the parallel story here? 有吗？有看到吗？ Okay. 还有啊，还没有停啊，我们 parallel story 还很长，一直到 quotient ring。等一下啊。So before we go to quotient ring, we need to introduce what? Homomorphism. Okay, so we have group homomorphism, we have ring homomorphism here. So group homomorphism, what does group homomorphism do? Then you map G to G prime such that phi of x plus y or equals to phi x plus phi y. Okay, depend on you want to use multiplication or addition. But ring is a map phi such that phi x plus y equals to phi x plus phi y, and then phi xy equals to phi x times phi y, and then you need to send identity, multiplicative identity to multiplicative identity. Okay. So if you differentiate what kind of identity you are looking at. Okay. And so just now we already mentioned, right? Actually not yet mentioned, but we proved that every kernel of phi is a normal subgroup. And every kernel of a ring homomorphism is an ideal. Okay. 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 Then what can we construct? What can we construct here is we can construct quotient group and quotient ring. Okay, quotient group and quotient. Some book you will see factor groups. I'm not sure. I think got factor rings. Okay. So what's the quotient group? So G mod n is a set of coset of the normal subgroup n. Normal subgroup n. And then quotient ring mod I, what is it? It's also a set of coset. Okay, but this coset I need to be careful. This coset comes from the additive part because our addition is a abelian group. Okay, so additive coset of I. So if I want to make a remark here is I is a normal additive subgroup. Okay. Okay or not? Okay. So that's why the multiplication that we define here, not that last time we defined what's the multiplication here, is a bit weird. A plus I times B plus I. Actually, it's just a subset of AB plus I, but we define it to be equal. Okay. Yeah. So that's why a bit weird. Yeah. Okay, because we're taking from the additive. So very strong, very important theorem here is what? First, isomorphism theorem. For both cases, okay, they are very important. First isomorphism theorem. Okay. So in the group, you have a surjective map G to G prime such that what? This map will factors through the canonical map. Okay, so what's the canonical map here? G quotient kernel 5. Okay, and then there exists a unique map that make this diagram commute such that phi equals to phi bar phi. On the other side, it's the same. Okay, you have a surjective homomorphism from R to R prime. Then it factors through a canonical map that maps to the quotient ring. Okay, so let's put this kernel as kernel such that this is the same. Such that this diagram also commute. Okay, now? Yeah. So just now we said that every kernel is a normal subgroup and every kernel is an ideal. The converse is true also. Every normal subgroup is a kernel of some phi. Every ideal is a kernel of some phi. How to realize this phi? What phi can you take here? You just take the canonical map. Okay, so you just take the canonical map. Okay, no? Okay, you just take the canonical map. Okay, so let me write down the punchline here. For every normal subgroup is actually the kernel, okay, of its canonical map. And then every ideal, okay, is the kernel of its canonical map. 什么意思啊？这是什么意思啊？ What does it mean here? It means that in this triangle, what do you take as your phi? Just take your phi as your pi. Yeah. Just take your phi as your pi. Then you see pretty obvious. Pretty obvious, right? Okay. Yeah. Not isomorphic already, actually is equal. Okay, equal is stronger than isomorphic. Does it make sense? Okay, if you let Any question? Any question? Okay. Yeah. Okay, next. Next important theorem is yeah, 对 correspondence, but 我看一下我 miss 掉什么。
没有 miss 到。
Okay, 没有 miss 掉什么。So correspondence theorem. Correspondence theorem. So in both cases, we will have correspondence theorem. And I want to tell you the very important thing about correspondence theorem that we didn't talk about the last time. So if you have a surjective map in a group, okay, what can you construct is the set of subgroup in G prime is in bijective correspondent or one-to-one correspondent with the subgroup in G that contain kernel of phi here. Okay, and then you have more information here. You know that this H is normal if and only if the image of this H is also normal. So let me define H bar to be phi of H. Okay, and you can count. Okay, you can count the element in H, which is equals to the cardinality of H prime times the cardinality of kernel. But what can you observe here actually? This says that a surjection on the group become a bijection on set of subgroup. Yeah, no. On this phi might not have inverse image. Sorry, might not have inverse function, but on here we have the inverse function here. What's the inverse function here? Send H prime to H. Inverse function, so you need to differentiate inverse function and pre-image. Okay, so I want you to differentiate inverse function and inverse image. Okay, these are two different things. Okay, so phi inverse become inverse function, okay, on the set of subgroup. Okay, this is strong, you know. 这很强欸. When you group things together as a subgroup, it becomes function. If you look at individual elements, it's not an inverse function. It's just a pre-image. 把你把东西 group 在一起看的时候，它变 function 了。这样了，明白吗 ？Understand? Yeah. How about the other side? So the other side is similar. It's kind of similar. So you have a surjection from R to R prime. Okay, and then where's the bijection here? Is about the ideal. Okay, so the ideal here. But the more important thing is about this quotient ring. So if you take your quotient, R quotient by the domain ideal, is isomorphic to R prime quotient not by I prime, where this I prime is the image of I. Okay, 这个比较重要一点。Yeah, 这个比较重要。Okay. So 这个 how to find this isomorphism? Whenever we write down this isomorphism, right, you need to ask yourself, who realized this isomorphism here? Actually, who realized this isomorphism? This is realized by phi actually. Well, I mean, to be precise, should be what? Should be pi phi. Okay, because you need to take away the I prime. And then this kernel, okay, kernel of this pi I prime here is equals to I. You know what am I talking about here? Let me draw a table for you. So R to R prime we use phi, and then R prime to R prime over I prime we use the canonical map, okay, on I prime. And then you should see that the kernel of this composition is I. Then you can use first isomorphism theorem. Okay. So composite of two surjection is still surjection. OK 吗？有问题吗？问题问不了，有问题卡住可以问。今天就是要问，白呢就问不了了啊，美春。OK， 要问就今天问。OK， 有两个。So next part. What can we do with two groups? We look at map between them. Now we can combine two groups. So one way to do it is we take product groups, okay, G1 cross G2, or on the other side, we also can take products ring. That's ring. Okay, so what's the product groups here? So G1 close G2 is what? All the tuple G1, G2. Okay, such that G1 live in capital G1 and then G2 live in capital G2. What's the LOC here? LOC here is compose components wise, right? Okay, compose components wise. And then what's the identity? Identity is just identity on both spot. Okay, and then there's a very important theorem here, right? When can you split a group into the product of two groups? When can you split that? I think you have a hard time doing this assignment question, right? So when can you split? What do you think? What did you show? You need to show that this two factor has what? Has trivial intersection, and then the product set HK have to be equal to the whole group, and also both of them must be normal in G. Okay, three things to check. Okay, product ring, product ring is similar, right? Okay, it's similar, really similar, really similar. So you have R1, R2 here, such that R1 is in R, R2 is in R2. And then what's the LOC here? Also compose component wise. 一样的，一模一样的。The identity is just identity on both spot. Same for additive and multiplicative. And 这里 product space 是怎样 decompose 的？这个很重要啊，这个一定有考。OK， 这个一定有考。So to know about decomposition here, we need to introduce an element called the idempotent. So idempotent is what? An element that satisfies E square equals to E. Satisfying E square equals to E. So why can we split this ring using this? Okay, let's say how to split first. Do you still remember the formula? R isomorphic to what? ER times Y minus E R. Okay. So last time, how do I motivate this E square equals to E? You should think about the projection in linear algebra. So if you project twice, right, you should get the same image. Okay. And then so you should think of this E like project this ring. So ER project rings to one part. Y minus E project R to the other part. Remember last time we showed that 1 minus C is also an idempotent. You try and square it, you still get 1 minus C. So it's also an idempotent. Moreover, if you take the product of these two idempotent, what do you get? E minus E squared, which is 0. So meaning they are somehow orthogonal. I know. So it's 3. Okay? 这个要读啊，这个有考。Last thing. So last thing. So the very important thing in group is group presentation here. So what's group presentation? We write G as a bunch of generator and then take out. Sorry, 讲什么？你讲哦，没有讲。正约，看你要什么？要讲吗？ OK， 后面放 relation good。So we introduce, I will write down the generator and the relation. Okay, if G is isomorphic to the free group, okay, generated by G1 up to Gn, portion out by the smallest normal subgroup generated by the word R1, R2 up to Rn. OK， make sense 吗？对吗？知道这个 N 跟 F 是什么东西吗？这个是 normal subgroup， 上面这个是 free group。Okay, it's natural we consider normal subgroup like what we tell you just now. Okay, if you send some word to identity, then it conjugate word also have to go to identity. But 另外一个在 ring 相对应的东西是什么？ 相对应的是什么 ？adjoint。OK，adjoint。So adjoint 做了什么事情？Just now I already told you, right? So R adjoint X over kernel of this phi. And let's say this phi is given to be isomorphic to R alpha, where f f alpha equals 0 and kernel of phi actually is equals to the ideal divided by x. 这两个也是会考啊，这两个。So important things inside here is what? So if fx has degree n, then what's the basis of R alpha here? What's the basis of R alpha here? Then 1 alpha up to alpha n minus 1 is the basis for R adjoint alpha. Okay, why is there no alpha to the n? Why? You can be reduced by your function, right? Because alpha n plus something else equals 0, so it can be reduced. Okay, similar for the higher degree. Yeah, I think these are the main point. So you need to take note of these, the last 4 chapters here. 我没有讲其他不会考啊，但是这四个你要注意一下。OK， 其他都很重要，是不是？读到这一边，你其实前面的都要把这4个就你要重点看一下。可以吗？有问题吗？今天我们很荣幸请到你的学长来介绍给你们一下我们的数学系的 ME， 因为你们下个学期 next sem you need to take ME right？ 然后我问你们到底拿什么 ME， 你们也是 blah blah OK，so 他们在这里他们会介绍你第一个，我让他们做的是介绍你 general topology。第二，其实这里他们不是完全是走 pure 的，也有不走 pure 的，所以你也可以问他其他的 ME 是什么个状态 ，OK 状况 ，OK 吗？OK 吗？OK，before 我们 go into 这个 section， 你们还有问题吗 ？lecture 的东西有问题吗 ？about lecture 考试。OK， 如果不敢问，先让他们 sharing 先 share 了过后，如果你们还要问，我们再继续。说你们可以问一下他们，你们 ME 要怎样拿，不要 blur blur 啊，不要 blur blur， 你知道吗？因为有学生告诉我他毕业过后他不知道做什么，课乱拿 ，pure max 拿一点 ，apply 拿一点，混出来是什么东西，你懂吗？所以你要 make your decision，OK？Yeah。说今天我不是要你做一个 decision， 但是我要你去问、去了解、是去咨询 ，OK？ 咨询他们 ，OK 吗 ？Yeah，OK， 要不要请金波？金波，金波，金波，你是有 slide 还是什么？你有 slide， 你要在我这边开吗？我 call 你哦，也可以，也可以，我 invite 你啊。
对吧？对吧？说这样讲，对吧？马上跟你讲，讲吧，什么？你讲什么？什么东西有跟？我没有听过人说。
这个没有，我这个没有。
没有。
OK， 给他讲完，我再跟你们讲有没有。我要check一下。我下意识都没有提到。等下我 check 一下，等他讲完我 check 一下。你们两个不要太讲到太 technical 啊！我要点名一下，我要 check 东西。不要讲到太 technical 了，他们睡觉了。就大概讲一下，讲一点他们懂的东西。拎多一点 MA1 的东西，他们比较懂。谢了吗？没有谢。
他们听得懂？
没有，他们有英文的，有2个英文的，说你要讲英文。
你给我一个
位置。
换位，做手点是。
哦。
电脑。
Okay, hello everyone. I'm Jingbo and I'm from MAT211 and I'm one of the senior and this course is MAT208 General Topology and will be offered in the next April semester to offer. Then topology is a quite abstract thing. The first thing that you guys need to know is what is topology. So according to this definition, I think something that you can know, collection, and then having some properties. You know this is called empty set, this is called the set, and then inside this collection. So this might be a little bit similar to your MA1. So your MA1 you learn closed set, right? So you know, I'm not sure you still remember or not. You have in chapter 1 or in chapter 1. So in chapter 1 you got empty set and whole real space in is closed set. So this one is a little bit similar but not the same. And then the second property, third property, close under arbitrary union, close under finite intersection. The close under you learn in Algebra 1, close under addition, close under multiplication. So close under addition is AB in the group, so A plus B in the group. So this one is also the same. AB in tau, so A union B in tau, A intercept B in tau. So this is what the close under arbitrary union and finite intersection. The finite intersection is like got finitely intersection, not infinite. So arbitrary means can be finite, it can be infinite. So this one is very important for you if you want to learn general topology. So in MA1, you learn whole thing in real space in 1 dimension. And in MA2, you will learn whole thing in Euclidean space Rn. So this is like n dimension. So you got 2 dimension, right? X axis, y axis, and 3 dimension, x axis, y axis, z axis. So this is like need to up to n dimension, a general real space. And then the more general thing is metric space, and more general again topological space. So in general topology, you will learn more about topological space. But before that, you will learn metric space first to have a better understanding. So, okay, this one is some summary of let's see MA2 first. MA2 is quite, I think, will be more easier than MA1 because MA1 is just for you to start learning the pure math thing, pure math stuff. And then MA2 almost the same with MA1 because in MA1 you learn the real numbers, but in MA2 you just learn the Cartesian product, just Rn. So just we will learn one more thing, Cartesian product, and then Cartesian product is like R times R times R, so it's like got coordinate, many coordinate. Okay, so you learn metric space, just definition of metric space, but in MA2 you all things focus on Euclidean space Rn. So this one, convergence of sequence, open set, closed set, neighborhood, interior, exterior, all things you learn in MA1, you will learn in MA2 again. It's about the same, almost the same. And closure is boundary is quite similar to boundedness. So in MA1, you know an open interval is bounded above by A, bounded below by B. So the boundary, you know interior is AB, exterior is minus infinity A, union B, infinity. So the boundary is A and B only. Just the 他们的那个坎就是我不知道怎样讲，就是 A and B. And then you learn limit point, isolated point, and then in chapter 2, MA1 and MA2 both continuity. So more or less the same. And then chapter 3, MA1 is another chapter, but MA2 more focused on sequential compactness and boundedness. You learn this kind of thing, connector compare, which is also you will learn in general topology. So, okay, come in topology. First thing you will learn Cartesian product, and then a very important theorem called action of choice. This one a little bit difficult for me, so you might be struggle. Okay, and relation and cardinality. You learn in discrete mathematics. You already learn in discrete mathematics, but in general topology with more deeper. And in metric space also, bounded, open set, closed set, neighborhood, interior, exterior, boundary, blah 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 blah. All things you are familiar with, but maybe different concept, a different thing, more general definition, more general theorem. And then in topology, almost the same, open, neighborhood, interior, boundary, closure, limit point. But what is their difference? So you know this thing. So metric space, you got metric space is distance. We call it a distance. We have a distance D. So in Rn, we calculate the distance in R is if AB, the distance is B minus A. If R2, the distance is x 2减 x1 square 加 y 2减 y square. This one you're familiar with, right? The distance in R3, R4, R5, Rn. Rn just x1, x2, blah 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 blah. The sum of the difference of the square and the square root. And then in metric space is like we define a distance, not just a standard distance like we learn in R2, in R3, in R. We will define ourselves the distance. That satisfy the axiom of choice. Axiom, sub axiom. I don't know. Sorry. Oh, okay.
Triangle inequality.
Okay, and more general topological space is a space without distance. So you cannot do something. You cannot have a definition with a distance. Like you have a open ball, you have a minus b, you got b minus a, but at topology space you didn't have this concept. You need to compute more general definition. Later I will tell you. And then 5分钟啊 ，OK 好，随便。So other elements like subspace topology, Hausdorff space is quite important in general topology. Later Seng will teach you if you take this course. And then homomorphism, product topology, quotient topology, you know product, what is called product ring, product, quotient ring, quotient group is related to algebra. Then, okay, these are similarity. Here I use green color MA1, red color blocks represent MA2, and black color blocks represent topology. So the Cartesian product is almost the same. In R2, you got this. So in Rn, you got this. So almost the same. It's the same, almost the same. So matrix space, I think your discrete mathematics learn symmetry, triangle, inequality, and positivity, right? Or linear algebra. So a matrix space is a distant function that satisfies these three properties. Then we will learn some concept called open ball. So the open ball, 我不要跳过，跳，让我来跳。Okay, topology, and then the topology is something like satisfy these three axioms, and then you will see that for the matrix space, this is actually a topology generated by the distance. And then this thing by Seng. And you will see like the closed set, and then interior closure neighborhood is not the same as you learn in MA1 and MA2, but it's related. Got the same theorem, got the same proposition. You see, then U is called open neighborhood as U is open set containing X. If U is an open set that containing X, so U is a neighborhood X. This is MA2. It's the same. Continuous function, this is what we call definition. So in your MA1 continuity, you use epsilon delta. So epsilon delta have a distance, right? But in topology, you don't have a distance. So this another definition for each subset V of Y, the inverse is open subset. So in MA2, you will also learn the same thing, but in theorem, not in the definition. The definition is still epsilon delta. In topology, there is no epsilon delta definition for continuous. Okay. And this is the last thing, connectedness and compactness. In MA1, in real space, you will learn closed and bounded if and only if sequentially compact in chapter 1, right? Okay. Then in chapter 2, in MA2, you'll be introduced one thing called compactness, and then you will know closed and bounded, sequentially compact, and compactness is equivalence. Then in general topology, you learn something like this. Yes. Kisan will teach you. And this is just a small part that I present to you. There are a lot of parts that you need to explore if you are interested in pure math. I think this one is a combination of algebra and analysis because it's an algebra course, but actually really need a basis of analysis because it's quite related to mathematical analysis. And if you understand what am I talking about, I think you can have a try. Yeah. But what I'm saying is like a simple concept, and although you don't know this course, but you know Kisan, right? So so he will teach you very details about general topology. So don't be worried. Okay. Just take it. Okay, thank you.
So basically, for those of you who are interested in pursuing pure math, I would say topology is a must for you to take. Like Jimbo mentioned, topology not only care about those space who have distance, but also consider those space that have no metric or no distance. So topology is a study of geometry structures, so under continuous transformation. So if you wish to study a higher level of geometry, or what they call manifold, you will see that actually topological structures actually come out very often. And on the algebra side, algebra topology is where you really get to see how certain properties get preserved. For example, the whole, or technically we call the genus of torus after stretching, bending, and twisting. Or you might think there's a topologist joke like how they see actually the donut and the mark is actually the same. So if you have chance to do research mathematics, you may find out that experts in category theory are building topological like structures on categories, which is a higher layer of abstractions on algebraic structures. So you will see more if you go deep into it. That's all from me. Thank you.
Thank you. Thank you for that sharing. So, Jimbo actually took 你还有什么你打过什么 ME 啊 ？Time series 啊？
没有。
没有。
Regression.
Regression.
Stochastic.
So if you have this sort of direction of ME, you also can ask him. Okay, he is a half guy. Okay, and this guy is a pure guy. So the pure guy is a half guy, so you can ask. Okay, how to take ME in a different direction. Okay, you can ask him privately.
Half pure, half technically.
哦，那个half是他不知道他为什么要这样做，但是他知道为什么他要这样做。So he know he know 你等下可以问他，你要问他，我不知道，你要问他啊？有全部人都想知道吗？还是你要私下问他 ？Why you take a half ME 啊？
Actually, what I coming here is like this school offer pure math courses, and I think in Malaysia didn't have a pure math courses offered by the university, so I come here to learn pure math actually, and then after that I found that it might be, I cannot say it's not suitable, but I think it put too much pressure on me, and also if I learn pure math, maybe it might be difficult for me to find a job or internship if I'm after I finish my degree. So like for me, pure math is like if you want to learn pure math, maybe probability, you will need to go up to master to PhD, so that you will have like a lecturer job. But if you learn pure math is okay, you will also like you can go to do a secondary school teacher, primary school teacher is also okay. So I learned statistics is like this market is like the society nowadays is more focused on business. So the data analysis part, the statistics part, I think is essential for me. So for me to find a job. So for me, I can have more choice to finding my internship, finding my job after my degree. So after I learning pure math, year 2, sem 3. After year 2, sem 3, I turn to learn stochastic regression and time series. So time series I will take in last semester, not now. Now I'm taking stochastic and regression. So I think there's not a bad choice as long as you know what you want to do. If you know what you want to do and you found that you are not in the right way, so you can change if the time is around. Yeah, you can do a change. Even though you can do a change in your master degree, so in here you learn pure math, and after that even though you found that pure math might be not useful to you, so in master you can turn to statistics, because as I know, if you're learning statistics, how can I say? They will accept you. They will accept a pure math student to learning statistics part, statistics stuff, something like that. They will more willing, because you learning pure math. You will learn more logical thinking. You will learn how to prove things rather than only computing something. Only computing. So pure math is teach you how to use your critical thinking, how to use your logical thinking to prove something. So that's all for me. Thank you.
Okay, so let me show you my LinkedIn. You see, I have my LinkedIn, right? I open up one of the message. What does this message say? Can you all read it or not? Yeah, ChatGPT, but so why this guy sent to me? So this is a 猎头公司懂猎头recruiting company consultant. So he asked me to join as what? As a quantitative researcher. What does a quantitative researcher do? You know? What does a quantitative researcher do? See. Enhancing our market presence across various asset classes. So let's see what are they doing. Can I see what they're doing? Yeah, actually it's on the quantitative finance side. Hey, he look for me. I'm pure maths. So why look for me? See, read what he wrote here, what they wrote here. You see, we recognize the individuals with a PhD bring a unique set of skills. What's this unique set of skills? Deep analytical thinking, intellectual curiosity, and problem-solving abilities. Nothing about finance. He didn't say you have to have a strong finance background. No. What they are looking for is these three things. And these three things can only be trained in pure maths. 我的意思是 train train 的意思是什么？不会变会。你在其他课是很难做到这件事情的。It's hard for you to get this kind of thinking unless you born with it. Unless you go through the other kind of training, maybe life training. But then because life treat you hard, so you get the skill. Otherwise, you need to train with max degree. OK 了，明白吗 ？Because max is rigorous, everything written out properly already. So your task is to read it, understand it. That's all. Okay. Once you can acquire this kind of skill from nothing to something, nothing to something, nothing to something, one day you go from nothing to everything. Something collect together become everything. Yeah, but I acknowledge that this process is pretty hard, very hard, super hard. But once you get through it, you will be a talent guy, talent person, talent person. OK 吗 ？Make sense？ OK 吗？听得懂吗？听懂我在讲吗 ？OK， OK， OK， but this one depend on you lah, depend on you. Okay, but this is just my view and my experience. Okay, I see across my classmate, my friend, also my student. Okay, it's the same story only. It's exactly the same story. Okay, happen and happen over again. Okay, but you really have to get this skill. These are the things that market want. OK， 不然你就是在比较低层哦，你是听别人做事，也可以，没有问题，也是 OK 的。但是如果你要做老板，你要 lead，then 你就需要这些特征 ，OK 吗 ？OK， does it make sense？ OK 吗？有动力读 abstract algebra 吗？Final 可以考来吗？有信心吗？有啊，题目我全部放在 lecture note 了，去找吧。OK， 确实 group action 不用放太多的心思。OK， 没有送你一个大礼物啊，帮我努力读了。OK， 还有其他问题吗？Any other question？ 没问题？没有其他问题？全村。
就开始做。
对，快点开始啊！快点开始，别来不及。他们还有问题啊？哎，你们有其他问题要问吗？他们还有其他问题要问他们吗？有没有升学的疑虑？如果不好意思，现在问你，等一下也可以私下问。有什么升学疑虑可以问他们 ？I think in future, Math Society should put this thing into your agenda. Otherwise, they are super confused as a student. Student council, student council. Sorry, student council. Next student council. I can put this into agenda. Sharing of ME. Yeah. Sorry, 你学过啊？Yeah. 对，继续学。OK 吗？有问题吗？没有问题就要考试见了啊。有问题吗 ？Online 有人有问题吗？只有招生吧？招生有问题啊？招生要不要跟你的同学 say hello？ 不知道在不在？No problem. OK 啦，如果没有问题 ，then good luck to the exam. Then we'll see you on next Friday. 我还不讲了吗？Group action 不用太那个，不用花太多时间。 Right, so see you on next Friday. Next Friday. 啊 OK， 你回去哪里？你家哦。Then 你之前呢？哇哦。